In this video here, we're going to take a look at friction and static particles. So when a body is in static equilibrium under the action of several forces, including friction, we must consider whether the body is on the point of moving or not. So for the first point here then, what we're saying is the maximum value of the frictional force, that's F max here. This is reached when the body you are considering is on the point of moving. And in this scenario here, we say that the body is in limiting equilibrium. And then for the second point here, generally speaking, the frictional force F is such that F is less than or equal to mu r. So in that case then, the direction of the frictional force is opposite to the direction in which the body would move if the frictional force were absent. So in terms of an introduction here to friction and static particles, those 2 points here are the 2 key points that we need for this introduction. Okay, so quite a quick introduction here, right? But we don't need too much more. So I think the best way to demonstrate this concept of friction and static particles is to take a look now at one practice question here. So for this question here, as we can see, right, we have a particle of mass 1.5 kilograms on a rough plane which is inclined at an angle of 30 degrees to the horizontal. We're told that the particle is held at rest on the plane by force of magnitude 10 newtons acting up the plane in a direction parallel to a line of greatest slope of the plane. We're then given that the particle is on the point of slipping up the plane, and we want to find the coefficient of friction between the particle and the plane. Now, as we can see straight away here for this question, we aren't given a diagram, so the first thing that we're going to do here for this question is just start by drawing our own diagram. Okay, so I've got the horizontal here, like so. We then have the rough plane, which is inclined at an angle of 30 degrees to the horizontal. So that would look, say, something like that. Okay, so this angle here then is given as 30 degrees. We have the particle on the rough plane, right? Like so. That's my particle here then, that is on the rough plane. So that would be the diagram for this problem here. But to go on and find the coefficient of friction here between the particle and the plane, what we need to do here is add the forces to the diagram to make this a force diagram. Okay. So the first thing that we have then for this diagram here is a normal reaction between the particle here and the rough plane. Okay, so adding that onto our diagram here, that will look, say, something like that. So we'll label the normal reaction here as R. We then have the weight of the particle, so it has a mass of 1.5 kilograms. So adding that to the diagram here, that would look, say, like so. That would be 1.5 G here. Okay. And for this force here, don't forget we need to also split this into components, like so. So what this does here is this forms a right angled triangle. Okay, so as we can see on my diagram here, this is a little bit small. So let me just quickly do this over to the right-hand side here, a little bit larger. So that's my force acting downwards here. That's 1.5 G, like so. And then we get the following here. Okay. So as we said then, this forms a right angled triangle here. We've got this component here, and we also have this component here. So for this component then, using basic trigonometry here, so this angle then, so this angle here is the exact same as this angle here. So this angle then will be 30 degrees. So in that case then, this component here will be 1.5 G cos of 30 degrees. Okay. And doing the same here then for this component, what we get here is 1.5 G sine of 30 degrees. Okay. That gives me my 2 components here. We're also told that we have a force of magnitude 10 newtons acting up the plane. So if I add that to my diagram here, right, that would look like the following. So that's 10 newtons acting up the plane in a direction parallel to a line of greatest slope of the plane. So that's 10 newtons there, like so. It should be parallel, but you get the idea. And in that case then, because this is on the point of slipping up the plane, what that tells us then is friction will act down the plane. Okay, so friction is going to act down the plane, like so. And we'll just label that here then as F. Okay, so that's friction there. And there we have it. So that's my diagram here, right? Labeling all of the relevant forces. So we now have everything that we need then to find the coefficient of friction between the particle and the plane here. So to get us started here, then let's just begin by resolving perpendicular to the plane here. Okay. So if we resolve perpendicular to the plane here, taking upwards as positive then. So in that case here, what do we get? Well, we just have this single force here R acting upwards perpendicular to the plane. Now considering what forces are acting downwards here perpendicular to the plane, well, that would just be this component here of 1.5 g cos of 30 degrees. And because that's acting in the opposite direction here, that would be negative. So we get R minus 1.5 g cos of 30 degrees. Okay. And this here then will be equal to 0. Okay. So we want to find the value of R here, the normal reaction between the particle and the plane. So in that case then, add 1.5 g cos of 30 degrees to both sides. In that case then, R is equal to 1.5 g cos of 30 degrees, like so. So just evaluate this here then using your calculator. And what I get then is 12.731 here. Okay, so 12.731 newtons there. That might be a little bit unclear. Let me just rewrite that. So that was supposed to be a 12. Let's try again. So 12.731 newtons there. So that's the value of R, right? Now, why are we evaluating R here? Well, because we know that the particle is on the point of slipping up the plane here, what that tells us here is that F is equal to mu R. Okay, so if we can evaluate R, which we've just done, and we can evaluate F, then we can also evaluate mu, the coefficient of friction, right? So we found R here. Now let's find F. So to do that, we're going to resolve parallel to the plane here. So if we resolve parallel to the plane then, taking downwards here as positive, like so. So what do we get here then? Well, I've got F going down the plane. I've got F. And we also have this component here, right, of 1.5 g sine of 30 degrees. So they're both positive because they're both acting down the plane, right? So 1.5 g sine of 30 degrees, like so. And what forces now are acting in the opposite direction then? Well, we just have this one force then of 10 newtons acting up the plane. That's going to be minus 10. And this is equal to 0 here. Okay. We want to find the value of F, right? So just, add 10 to both sides and subtract 1.5 g sine of 30 degrees off both sides. So in that case then, what we get here for F is 10 minus 1.5 g sine of 30 degrees, like so. Again, just put this into your calculator here. And if you do this correctly then, what you should find is we get 2.65 newtons. So we get 2.65 newtons there. Okay, so as we've mentioned then, we've evaluated R here, we've evaluated F, so we can now go on to find mu, the coefficient of friction between the particle and the plane. Okay, so in that case then, so using F equals mu R here, like so. So F is 2.65. What we get then is 2.65 is equal to mu times by R, which is 12.731. So 12.731 here, like so. And in that case then, what we can see here for mu, the coefficient of friction, right, is we get 2.65. So 2.65 all over 12.731. 12.731 here. And again, if we just evaluate this here using our calculator, what we get then, if we give our answer to say two significant figures here, is we get 0.21. Okay. And that is to two significant figures here. Okay. And there we have it. So the value here for mu, the coefficient of friction, seems sensible, right? It's between 0 and 1. Just give it a quick sense check. So that's fine. And there we have it. Yeah, so that gives us the solution there to this one practice question here for this video. And that brings the end then of this video here on friction and static particles.